Alright, day 23. So I have some ideas as to how to improve collision detection. So, alright, what are we doing? Given a sprite, our starting point should be the current position and the delta. So current position v2 delta position is something. Now, alright, test position is not that. Alright. Okay, there we go. So we have a current position, we have a delta position, which we get from somewhere, in this case input. Yeah, depending on what the sprite is, it's going to come from different places. Given those two things, we can work out the test position. And not the test position. Well, yeah, so given those two things, what do we know? Let's just comment all of this out. Yeah. So given those two things, which is the current position and the delta position, this and that, yeah, this is just where the delta comes from. In this case, let's section that off. Current position, alright. There we go. We need to go into a loop. And once we break out of the loop, we know that the position has been resolved for this frame. Given the position and given the delta vector, we've resolved. Breaking out of the loop means that we've resolved the position by modifying those. Well, I guess we're gonna resolve the collision by modifying current position. So we're just gonna say, once we break out of the loop, just set this to current position, like that. Okay, so we're not gonna be doing this actually. So we go into a loop, and once we break it, so basically, like, how do we know we've resolved the collision? Well, if we didn't collide with anything, bool collided, false. If not collided, break. Okay. So if I just compile and run this, then we will not collide with anything ever. Nor will we actually walk around. Well, actually, come to think of it, right? If we didn't collide with anything, that means that we can just current position, we can add the delta to it. That. Okay, so now we can move around. We're not colliding, because the code that's supposed to do the collision detection isn't doing anything. Alright, so how do we work out if we've collided? Well, by iterating through all the collision lines, which is this loop, essentially, except that I'm gonna change it a lot. Alright, so that is the collision line, and we need to do something to figure out if we've collided with this specific line. Okay, let me just open up something here. Alright, so, I mean, yeah, that works. Okay, so this is the delta. I mean, this is... Alright, I need to label some things. That is one big. Let's label the points. What are these outlines? Oh my god. Oh Jesus Christ. Okay, let's just remove that. Let's, you know what, let's build it up from... So 5 is the arrow, alright. And apparently I can attach text to the arrow, it's like... So if I put it here, it's independent. But if I put it here, then it's also independent. Now it's not independent. Interesting. Well, anyway, so... Oh, fuck's sake. Maybe I should just turn that off. Is that turn offable? No? No. Okay. So let's say A is a point. Can I draw a point? Initial position. And then we have another point. Final position. Call it B. And then there is this vector, which is that delta position. Call it D, I guess. Oh my god. No, no. Can I select can I select D specifically? No? No. Oh, I can, kind of. Okay. Oh, maybe, well, maybe. Alright. Initial position, final position, delta. Now, we can have a wall that sort of gets in the way. Oh my god, no, that's free form drawing, I don't want that. So let's say there's a wall that gets in the way. And I mean, the way we're defining walls is by like having a reference point and a direction. So and it might actually be easier to write collision between any two arbitrary line segments than it is to use the fact that we are axis aligned. So I'm gonna try that. Okay, let's label these. So that point would be, I guess, C. And maybe draw it like blue or something. There we go. Yeah, why not? C and D. Okay, that's the wall and that's the movement. This right here is the normal. N, that's the wall normal. And I suppose we can have a vector that's perpendicular to that as well, which is like the unit vector that points in the same direction as this line segment points. So out of our wall definitions, we're not storing normals and stuff, but we can construct them easily. Out of what we have. And these 2 points, I mean, we're storing one of them in the lengths, which means that we can get the other one pretty easily as well. So given the 2 points of the wall segment and the normal to that, what do we want? Well, one thing we can do immediately is, given this vector d, well, one thing we can do is actually define some more vectors, like this one. And this one. I need to, I guess, label them. Oh my god, no. A and B. Those labels aren't used, I don't think, right? There we go. So A and B are just vectors from our initial position to the wall reference point, and from the final position to the wall reference point. Now, if the dot product of A and N is, in this case, negative, if N is pointing up like that, is negative, that means that the initial position is on the side of the wall from which we could collide with it. Like if A, oh my god, if A is on the wall, then the dot product is 0. If A is behind the wall, then the dot product is negative. I mean, positive. Well, like it's like here, the dot product is positive. So for B, the dot product would be positive, and for A, the dot product would be negative. And okay, maybe can I write this down? Let's see. It's like A dot. If only I had a dot. Is there a dot? Not really. Well, A dot N. We're gonna just use that dot. Period. So if we do A dot N, it should be either negative or equal to 0. That's A dot N, this one. So that check will immediately discard all movements that start from behind the wall. Because if we are behind the wall, we can't possibly collide with it. Okay, so another thing we can do is B dot N is positive. Strictly positive, right? So this second check will discard all movements where B ends up being in the wall or in front of the wall. Because if we are starting from here and we are ending here, then we know we definitely haven't collided. Okay, so just with these two checks, we are limiting it to the cases where we start in front of or in the wall and ending behind the wall. Okay. So we know we've crossed the wall, we know we've crossed the line on which the wall resides. What we don't know, though, is whether we crossed this line segment specifically. So there could still be a case like this. Like this. Oh, I guess on the other side it'll be a little easier like that, but then it crosses the end. Anyway, maybe the wall should be shorter. Actually, never mind. So that crosses the line on which the wall resides, but it doesn't cross the actual line segment. And these need to be discarded as well. And those, I think we can discard them pretty easily, right? We can just look at we can look at what exactly? Well, I mean, if I draw another vector that goes from A to D like this and call it well, not D, AC, guess. So this vector. Okay, so if we look at vectors A, C, and D, the outer product. Oh, there we go. All right. So the outer product of D and A is gonna have a different sign to the outer product of D and C. Whereas for a case where it doesn't cross the line segment, well, that still crosses. That doesn't cross. So for that case, this D and A and D and C will have the same sign. So these things need to have different signs. And I suppose the edge case is like when is when one of them is right on the edge and it's 0. And I guess that's just the rounding rule issue. So if you just multiply these, if you just multiply the outer products, if they have different signs, this will be negative. And if one of them is 0, then, well, they can be both 0. But if one of them is 0, then, like, whether we collide with, like, that edge of the wall will depend on whether this is greater or equal. I guess greater or equal. So if one of them is 0, that means that we are right on the edge. And outside of that case, if they have the same sign, then this will always be positive. If they have different signs, this will always be negative. Okay, so with these 3 checks, we are now limited only to the cases where we're starting in front of the wall, or in the wall, and ending behind the wall, and we are actually crossing the segment. And at this point, what we're trying to get out of this is when are we crossing the segment. So we have the initial position in the delta, and we want to know where this happens in terms of like proportions, right? So like f equals it would be a dot n, the dot product of a and n, and well, I guess it's the absolute value really, right? It's absolute value of a dot n divided by the sum. Like the yeah, we really want the magnitude there. A dot n plus b dot n. So it's that. So given these 3 checks, this will be the proportion this will be the proportion of this vector that we need to go to hit the wall. And I suppose our collision detector really needs to provide us with that proportion, and that's that. And I think that'll be kind of enough-ish. Okay. Well, it's enough to start anyway. Alright, so given this arrangement, what's the first thing? Well, the first thing is to figure out what the... So we already have this, we already have this. We know we're gonna need a dot n, so we kinda need an n, which is the normal. Okay, normal would be v2, v2, normal, I guess wall, normal, oh, what? wall normal. Is that like, no, that's not that. Some weird key combination. Okay, wall normal is we somehow need to determine it. Wall normals collision line type. So we'll just have one of these for each of the types. So that is this. Well, let's just add a count and just have v2 wall normals is, and then for each of these there's going to be an entry. So if it blocks from top, then the normal points down. So it's 0, minus 1. And if it blocks from bottom, then it points up, so it's 0, 1. Of course, yeah, y up versus y down is... I mean, y is up right now in world space, so yeah, maybe we'll keep it like that for now. Block from left, bottom points up, top points down, left points right, I mean left, block from left, like left points top, block from top. No, I think no. Block from top, that's this case, right? Yeah, it blocks from top, so it points up, so it points to the top. This points to the bottom, left points to the left, so it's minus 1. And right points to the right. Okay, so we look up the normal. Okay, now we have this. Now we can do a dot n. Which is like current dot wall normal is v2 dot current position and wall normal. Come on. So we have all these things. Yeah, I mean f32 v2 dot return v1 x times v2 x plus v1 y times v2 y. Okay, so that is the dot. That's this thing. So if that's less than or equal to 0, then we need to know what B is. So v2 B is new position. New position is v2 add current position delta position. and then f32 new dot wall normal is v2 dot new position wall normal. Okay, and that has to be greater than 0. Okay, now onto the outer product. So we have D, we have A, we don't have C. Well, to have C we need D. Wait, do we have A? No, we don't have A. Oh, we don't have A. Yeah, or B actually. V2, hold on. So we actually do need to work out what A is, because this is a vector from the current position to where the reference point on the wall is. Wall bound 1. Let's go with wall bound 1 is collision line left. Okay. So we have wall bound 1, that's this. Now we need to have A. So A would be this minus current position, right? Bound 1, so it's like V2 sub current position. Current to bound 1. Yes, if current position is like 0, then this is just what that is. Yeah, that makes sense. Like this, wall bound 1 minus current position. Okay. That's A. That's this vector A. Now A dot n. That's what we need to. It's not current position. It's current to bound 1. That needs to be dotted with the normal. So that is new position. Then we need to do v2 new to bound 1 is v2 sub wall bound 1 new position. And it's this, right? Wall bound 1, current to bound 1. Okay. So new to bound 1 dot with that's b dot n. So we had this far in. New dot wall normal. Yeah, so that's this. Okay, now D we've got, that's delta position. A we've got, that's current to bound 1. C is current to bound 2. So we need to know what wall bound 2 is. V2 wall bound 2 is something. Well, presumably what it is just wall bound 1 times well, not times, wall bound 1 plus v2 scale, and what we're scaling is like a wall unit vector. So if we take the wall unit vector and scale it up by the length, and then add that to bound 1, we'll get to bound 2. Of course, we need the wall unit vector. Wall unit vectors. Okay, so block from top. Well, that's this one. So unit vector would just be pointing to the right. So like 1, 0. Block from bottom would also be pointing to the right. 1, 0. It's the same for them, right? And these ones, left and right, these ones would be pointing like up or down. Left, right, so let's say they're pointing up, so just like 1 and 1. Of course, well, it has to point specifically, like it depends on where the bound 1 is, right, kind of. Bound 1 is either top or left of the wall, which means that for the horizontal ones, it should be pointing to the right, so that's correct. But for the vertical ones, it should be pointing down. To go to bound 2, because we need to decrease y to go to bound 2. Okay, so wall normal and then wall unit vector. Okay, and of course we can just do that v2 add. Okay, so now we know what bound 2 is. That's this. We can work out current to bound 2. Is v2 sub okay, so now we know this current to bound 2, so we can work this out. Alright, so F32 what? D outer A. So that would be delta outer A is v2 outer between delta position and current to bound 1. Yes, let's write v2 outer. Yeah, v2 outer, for any, like, these are two-dimensional vectors, right? So a two-dimensional vector A would be essentially like ax times x, like x unit vector. How do I represent a unit vector? Like, let's say it's like ax times x, capital, why not? Plus ay times y, and the outer product is worked out between, where's the there it is, between that but b instead of a. So it's b and b. Well, what we've got here is ax, okay, this part, well, I've got this part, this first product, which is x wedge x. So x wedge x is going to be 0. So that part goes away. What doesn't go away is ax by. That doesn't go away. But what that is simply ax. I mean, I guess I need to. Well, do I? I kind of do. Ax by, and then x wedge x, right? X wedge y. I mean. And yeah, that's kind of like a, yeah, there we go. So that stays. And then similarly here we have aybx, y wedge x. So aybx, y wedge x. And then this goes away because it's y wedge y, which is 0. And now y wedge x is minus x wedge y. So minus x wedge y, there it is. So the end result of this then is what? X wedge y, and then in brackets we've got ax by minus ay bx. Yeah, so ax by minus ay bx. Ax by minus ay bx. Right, so there's delta outer A. So what was the point of this? Delta outer C. Okay, delta outer C. So C is wall bound, current to bound 2. Delta outer B1, wall bound 1. Delta outer bound 2. There. And they need to have different signs. So that's the product of them. And what did I say? Less than or equal to 0. Okay. So once we get down here, we just need to work this out. So a dot n, we already kind of have that. That's current dot wall normal. Except we need absolute value, right? I mean, I guess I can just work out all the magnitudes here. And nu, like that. So we work out the magnitudes of these two things, and then we just do that first one over the sum. Like collision proportion or something like that. Okay, so that's how far in we've collided. And so we need to do that for each wall. For each collision line, what I'm calling, and work out which is the closest to us. So F32 collision prop is 1.0, let's say. This collision prop is that, and then collision prop is min between itself and this one. Now, at this point, we actually know that we've collided for sure. Collided through. Yeah, so if the product is less than, I mean, after all three of these checks, we know that if this is true, then we've collided. Okay. So once we go through all the walls, if we didn't collide, then just do that and break out of the loop. Now, if we did collide, then it's something else. So that's what happens when we don't collide. That break should break out of that loop, yeah. So if we collided, that means that this proportion, actually I need the absolute value, hold on. I mean, min and max will help as well, you'd think. For some reason we don't have those, okay. Abs val is x, let's just wrap it in so many parentheses. X greater than 0, no, it's smaller than 0, question mark, minus x, otherwise x. Okay, so if we did collide, then we need to move this current position, yeah, we have a current position that we're modifying there, right? Well, we're not modifying it in the loop, but we need to modify current pause and delta pause, and then go through the loop again. F32 clipped delta is V2 scale, I guess, and delta position collision proportion. That's a V2 clip delta. Then current position is V2 add. Current position clipped delta. So we add clip delta to the current position, and then the delta itself. Okay, what happens to the delta itself? Well, okay, well, first of all, let's see, hold on. So the delta, modify delta and loop again. So that's what needs to happen, but for now I'm just gonna break. Okay, let's see, do we collide? We collided with that wall, so that's something. Okay, is that like, are we passing at the top, or what's happening there? I think that's what's happening. Yeah. So the walls are sticky. We can pass through the wrong way. Yeah, if we collide with one, we can't move anywhere. Colliding with the top wall, yeah, the left, that, yes, bottom, yeah, okay, so the collision is working. Except that this part is what we need to do now. Okay, so once we find out what the collision point is, I guess that's a new diagram. Let's gonna use some of this. Yeah, let's just remove that. Well, I mean, C and D we still kind of need. So once we find out what the collision point is, what I kind of want is I want to take this delta and move it. It's like I want to redirect it here, and we can either like rotate it or dot it, or like bounce it. But I guess I'll just dot it. So okay, so what are we dotting exactly? So first of all, let me just label A, B, C, D, and A, B, C, D, E. That's point E right there. So the whole thing is D. Oh my god, what the fuck? So the whole thing is D, but this EB part is something else, like call it little e. Okay, so we need to take little e and dot it with, actually we kind of do need normal still. But this time it's not the normal that we are dotting with, it's actually the wall. It's the unit vector that points in the same direction as the wall. So we dot with that. So this would be what, E dot so there is another vector here that points, call it G or something. Okay, so E dot G really is what it is. So this thing is E dot G is what we need to work out. So we have G, that's the wall, you know, whatever I called it, wall unit vector. Yeah, wall unit vector times E. So what's E? Well, V2 remaining delta. Remaining delta is V2 scale delta position by 1 minus collision prop. I guess I need at this point to like make sure that collision proportion is within the expected bounds. Okay, so the remaining delta is that. Now, to remaining delta dot wall is V2 dot, and it's the dot product of remaining delta and wall unit vector. Yeah. Oh yeah, so we need to save the wall unit vector then. So wall unit vector. Okay, so if this collision proportion is smaller than collision proportion, then accept it and set wall unit vector to wall unit vector. I guess this should be called collision wall. Collision wall HB. Collision wall unit vector is wall unit vector. Yeah, wall collision wall unit vector. Wait, hold the dot product, yeah, the dot product tells us how much remaining data delta F32 along wall is that, and then we just do F32 V2 remaining delta modded is V2F scale wall unit vector with and by that factor, and then we just do delta position is remaining delta modded, like that. So we modify the delta, we modify the clip position, and then we loop again. Okay, let's see, what does this do? This lets us move along walls. Yeah. Yeah, we can't pass through that corner as expected. Okay, so the walls are no longer sticky. Okay, well, that is... Okay, alright, grounding, make walls not sticky, we did more than... Yeah, so that we still need to do, that we still need to do, that I kind of did. I'm just gonna remove this. And yeah, compile, run. Well, I mean, yeah, that's fine. Alright. Focus into primary sidebar. Yeah, that's fine. And that we don't need. Yep. Yeah, alright. Improve collision detection. Okay, how many to-dos did I leave? A lot. Maybe. Yeah, obviously. That's not... Yeah, okay, so I kind of want to draw what we're colliding with. Alright, well, where do I even draw collision stuff? Here. Oh yeah, I'm just pushing it into the screen rects path. That's to draw the walls. I'm not drawing what I'm colliding with. Well, I mean, I'm just colliding with the one point that's on the sprite. I mean, it would be useful to draw the offset, just in general, I guess. Okay, how do we draw the offset? Anything we can do in the shader? Probably not so much. Yeah, shade, yeah, probably not. Index top left. offset. Yeah. So the offset is passed in. So if I could just, like, say, draw a little rectangle where the offset is. Can I just do that? Unclear. You know, maybe what I should have, though, is instead of relying on this sprite scale multiplier, I could pass in a scale and then just scale things up however. The blend assumes square pixels though, so I mean, I suppose if you're sampling from should that be a separate pass or should I just pass a scale? Because right now this is used in one place, right? Essentially. Well, it's used to determine what the camera is supposed to be seeing. But then there is also this assumption that we can take this texture in the atlas and just scale it up. Whereas in screen rectangles, we don't really have that. We don't really have that assumption there. Yeah. The offset also changes depending on what animation it is. So if I were to draw an offset, I would have to go through what would I have to go through actually? Let's see. Well, I mean, right here, interesting. So right here, we are pushing in these sprite tracks. At this point, we kind of know what the offset is. Because the offset comes really from text and atlas. So as I push in the sprite rect, it's like, well, we know what the offset is, so we know what to draw. We can't modify texture. Well, I mean, unless we want to rebind it. So yeah, it's almost like at this point I want to just push another sprite in. Except that sprite is just going to be... It's not a sprite. It's just... a rectangle. Right at the position where the offset is, and then it's just centered on that. But that would require a different pass through. Yeah, if I want to draw if it's just a square, then, well, the square we can manage. We could also just go through the screen rects and just translate the offset into what the screen position of it would be and submit a screen rectangle. And just draw that on top of everything. I mean, I guess that'll work. So maybe I should just do it then. Well, this is the position determination. So if I just take this out to, like, what sections do we have? Miscellaneous, input, miscellaneous, and platform. Okay, well, miscellaneous, why not? Static, v2, world to screen. Like, what do we need? Return, pause, screen. Well, clearly, okay, we need game. That's gonna be game. And this is the point that we're actually trying to move around. Game. Well, v2 position game, and then i32 window width, i32 window height. Just that. World to screen. V2 pause scr. Is that game window width, window height? That's not, I mean, that doesn't change anything. But being able to do this now, we should be able to draw the offset. Okay, so we copy screen rectangles here. So the first thing is to copy sprites, and then each time we are also going to add a screen rectangle. Offset rect. Maybe, come to think of it, maybe this should be, so v2 world to screen, oh, world to screen v2, static rect world to screen rect, and presumably it's gonna take the same stuff. Except this is gonna be rect. So rect, the result is top left world to screen v2. v2 rect top left, and dim is rect, well, I mean, I guess it's just scale v2 scale rect dim sprite, game sprite scale multiplier. Turn result. Game window width, window height. Can I put a comma here? Yeah. So thickness 5. Dim is that. If vertical, then dim is this. And maybe I can just do like rect collision line rect world is collision line left and then just here go rect collision line rect screen is world to screen rect, and then this is gonna be collision line rect world, and game window width, window height, like that. Where is game defined? Maybe I should just do it this way. Game. There we go. And wherever it's passed by all of these things, just need to do that instead. Okay, collision scripts, collision, oh my god, collision line rect screen. What's the error? Yeah, let's not do that. Oops. How is this even allowed? And take the address of itself. Like, who wants that? Yeah, now it's compiled. Okay, well, that is one world unit, by the way. Alright. That seems to be working. Also, we have that generic thing. Maybe I should try using it. CPP reference generic. Okay, apparently that's how it works. Okay, so like I can do what? World to screen. Generic X long double. Okay, well. Instead of long double, it will be like v2, right? And v2 is that. And then rect is this. And there's no float. Oh, I see. Except that this is like X, and then game, and then window width, and then window height. Oops. It's like that. And can I just call that? Like, does that work? Maybe. No, it does. But that's just, that seems kind of pointless as a feature. But, I mean, it works, so whatever. How's the debugging experience? Yeah, I mean, it's fine. Now that means we can do lerp like this as well. Let's see, can I remember how to do this? Define lerp from to by, and then like parentheses, and then from to by, and here we do underscore generic from, and what happens after? Comma, of course, comma, then that's type name, like F32, then it's colon, and then it's function name, comma, right? There's no default, comma, v2 lerp, v2 lerp, what's that? Lerp f32, and let's see, apparently there is an error somewhere. Oh, no, it's generic like this. Like that. Man, the syntax is just so good. Does that work? No. Oops. I mean, we do have lerp defined. Except, wait. No, it's like that. There. Okay, what's this? It says lerp undefined. Oh yeah. So v2 lerp. Do I actually call it? No, I don't call it anywhere. I see. Can I define it like before? Maybe? Maybe. Does that mean I can just use lerp here? Does that work? No, it works. Interesting. Huh. Alright. Collision line rect. World to screen. So the whole point, well actually, now that I'm here, you know how we have this rectangle yeah, I might as well write some functions like static rect shrink rect. You know, it's not really, you know, helping me, the fact that this is multiple lines. Rect shrink. Turn rect by. Top left is v2 sub, I guess. Rect top left. V2 add. And then dim v2 sub rect dim v2 by times 2 by times 2. I mean, maybe I should just do then static v2 from f32 x return v2 xx. Define v2 from. Actually, this can't be done this way. Unless there's always one argument. So then, yeah, well, variadic. Yeah, variadic function arguments. Like maybe there is actually. So now this could be v2 from f32 by, and this is v2 from f32 by times 2. Like that. shrink. Oops, game. So that, and shrink it by 2. Or by 1, actually. Yeah, so that still works. Yeah, speaking of those variadic function arguments, can I just take this here and like pass it on somehow? Like, is that something that I can do? No? Expected expression, yeah. Because that will expand to exactly those 3 so I think this is like VA args or something. VA args. C macro variable arguments. What's the syntax for that? Underscore underscore VA underscore args underscore underscore. That. Oh, yeah, that just works actually. Well, that's pretty good. Okay. Yeah, well, the whole point was to actually do this. Offset rect. What's the offset rect? World. Top left is going to be what? Sprite. Common top left. V2 add. Sprite common top left. And what are we adding? We're adding that offset, which is sprite rect text and atlas offset. Oh wait, hold on. That is an offset in pixels. Yeah. Top left rect world. Dim is v2 from f32. Yeah, we're not adding anything. Okay, so that's the top left of the sprite in world space. That's the dimension world space. Now rect top left rect screen is world to screen top left. The autocomplete is helpful. Top right screen world, and then game window width, window height. Okay, well that is one problem with these things. The autocomplete doesn't work. Well, I mean it works, but it only works for the macro. Top left rect screen is that. Then we do rect offset rect screen is rect translate top left rect screen and translate by the offset, which is atlas location lock atlas location, like that. Atlas location offset. Okay, rect translate static rect translate rect v2 by return rect top left v2 add rect top left by dim is rect dim top left. There we go. What's wrong here? Oh yeah, I didn't put a comma there. That's what's wrong. Okay. Now we have the screen rectangle, probably. So we can probably push this in. Offset rect screen, Jackson Atlas white pixel. Color is that. Why not? So that seems like it's doing something. So is that what we're colliding with? Seemingly yes. So there it is inside the wall, they can pass through fine. Okay, let's just reduce the speed a little bit. Seemingly we can. So we can't side on collide, but that's kind of by design. Oops. Oops, that's not the right one. No, that's also not the right one. There it is. Okay, well we seem to be colliding correctly at least, so that's something. Of the zoom or nope. Yeah, now I'm out of the zoom. Alright. Okay, so that's me drawing the offset. It's not necessarily drawing the well, I mean, right now we're colliding with the offset, so in that sense, we are drawing what we are colliding with. But another thing that's interesting is, are we drawing the offset correctly even? To draw offset, like at some point I need to figure out a better way to draw that. So if we enable animation and stuff, which at some point got disabled. No, grounded. We're not handling grounded. Yeah, so the offset changes there, and I think that is correct, because the offset for the running one is actually 3 pixels in roll space. So yeah, I think we are drawing it correctly. Alright. World screen. Game. Yeah, that's fine. Some string is being drawn here, apparently. Okay. Yeah, I don't think that one is even really doing anything. Because, like, yeah, we don't see it. Yeah, so that one's not doing anything. Let's remove it. It's fine. Okay. And draw sprite offset. Alright, well, that's gonna be all for today. Thanks everyone.